All right. As always, I'll start with some announcements. We have our first assignment due on Wednesday. I've already seen lots of great questions from people, but also I see that there is certainly the level of back and forth that I would expect from the class. So if you have not yet had a chance to get started on that, I would recommend entering panic mode and getting started as soon as you can. It is not a one-day activity. It is something that you'll start, get stuck on, iterate, come ask me questions, keep making progress, get stuck again, and success will come through repeated iteration in order to understand it well enough to be able to perform well on an exam that's going to be a week from Friday already. This is the start of week 2. So what you can expect for that is you will have a study guide by this Friday, and it will cover material from the next assignment as well. I will do what I can to get that turned around quickly. That's going to be a challenge, but I think we can get there. It'll be really important for you to advocate for yourself and make sure that you get what you need ahead of that. I will have extra long office hours as needed to make sure that I'm able to get to everyone at a time that works well for you. So get started early, and I will have hours of office hours to make up for everything that I can't get to at the level of intuition that I would like you to be able to have from that back and forth. Any questions about the content from last week? Any clarification questions on the homework that I can give, or any other feedback about how the class has started so far?
Exam 1 is going to cover everything you've done as well, right?
Probably not. Probably whatever's on this next homework, that's going to be where I would put the cutoff.
Like I get taught something on Thursday and get tested.
Yeah, no, I do not. I try to only cover the material on an exam that you've had time to get a study guide for, iterate on the study guide, and ask me questions. I like to also turn around any homework for that content to whatever extent that I can. This is going to be the most challenging class to do that for, though, because the sheer quantity of students we have and limited number of hours between when it's submitted and I may try to put the deadline a day earlier if I do that, because then that would just give a little bit more time for some turnaround and some feedback on that. Maybe what I'll do, I tend to do this from time to time as well. I can set 2 deadlines. The deadline for you will get feedback will be 1 day, and the deadline of you'll still get credit for the assignment, but no guarantee. Kind of the turnaround would be on an as able to basis for that. So I can look into that as well, kind of having a either Monday or Tuesday deadline if you'd like to have that turnaround, and a Wednesday deadline as usual if you're okay with or can't get it in at that point. Other questions? All right, we're going to dive into the next fun topic, which is we're going to be converting between NFAs and DFAs, because I asserted that these 2 types of automata were equivalent to each other, but we actually need to go show that, as well as introduce an algorithmic process for converting from one to the other. So we'll start by just stating that a DFA is really just a restricted NFA, right? We said that an NFA was exactly the same thing as a DFA with 3 additional rules that you could implement. So if you disallow those rules, you restrict the NFA back into the rules of a DFA. You can think of kind of taking small snapshots of pieces of DFAs and then turning those into potential NFAs, and you would realize that there would be an infinite number of NFAs that you could create for any DFA or part of a DFA. Let's ask about the converse. From discrete, you remember the definition of a converse? If the statement is A implies B, the converse is?
B implies A.
B implies A, yeah. So if we say, all right, well, we can restrict an NFA, a DFA is a restricted NFA. Can we say something about, is it possible to have multiple equivalent DFAs for a particular NFA? We can create many NFAs for a DFA. We create many DFAs for an NFA. Any thoughts on that? Any intuitive, I think the answer is yes, or I think the answer is no, even if you can't really fully explain it at this point, but just a thought based on how these structures work?
Take a stab at it, just.
Yeah.
Break the silence. I want to say intuitively no, considering there's a many to one ratio of NFAs to DFAs. I think going backwards is a lot harder to get
Yeah.
a DFA that replicates something as an NFA, because a NFA has stuff running at the exact same time versus DFA is sequential. It has to run at this point.
Your intuition serves you well. There is exactly one DFA for an NFA. There is no real optionality at that point, which means that it's a great process for an algorithm. We can just state, here is how you derive the DFA that represents this NFA, because there's only one of them. There could be multiple NFAs that all map into the same DFA, but you cannot have any branching from there. That DFA is the DFA that represents that NFA. Let's now start to think about what that algorithm might look like. I'm really going to start querying people's intuition here, because I don't fully expect you to come up with this algorithm. But if I were to give you an NFA and ask, what would the DFA that it represents look like? What would we need to keep track of? How would we start that process? Yeah.
Because you have a lot of unmarked, you know, the arrows, the unmarked
Yeah.
arrows and NFAs. You'd have to have all those arrows going to trap states.
It's an intriguing idea. There's actually a way around that, but that would otherwise be true. Like if you can teleport, what does that mean about in a DFA? You cannot do that. How would you represent that? Thinking about the challenges that an NFA has associated with it, how would you map each one of those changes to something that is legally able to be done by a DFA? One idea would be, if we can't do that, then we need to introduce a trap state. But even then, what if that lambda transition was the reason that we were able to get to a final state? If we go to a trap state, we can't get out of that trap state, we can't accept that string. How can we do that? Any ideas about, especially for lambda transitions? What does that mean about the associated structure of the DFA that is equivalent to it? The answer basically is the DFA is going to be larger than the NFA. There are going to be more states, and those states actually represent, yeah?
Well, because if you have the lambda transition, don't you have to take the entire previous part and kind of duplicate it and then add more to it? So you have like, it would be way bigger, right?
That would be the brute force way to do it, but I think that would work, actually.
So is there a more intelligent way to do it?
Utilizing set notation and sets. So each of our states in the associated DFA is not going to represent being in a state in the NFA. It's going to be representing being in a set of states in the NFA. Let's take a look at what that seems like. So in the very first NFA that I introduced, where there was a lambda transition from Q0 to Q2, we could teleport between those. There's actually going to be a state in the associated DFA, and that state says that I can either be in state Q0 in the NFA, or I can be in state Q2 in the NFA. So we're going to make states that represent sets of states in the NFA, and that's going to become the states in our DFA. Let's try to intuitively understand it. After a DFA reads a particular string, it can only be in one state, right? If we, according to a DFA, when you're in a state and you read a character, there's only one possible transition. So we need to be able to convert all of the NFA and its possible branching factors. It can either come from two different A's with edges out from the same state, or a lambda transition for a teleportation. We need some way of breaking that down to saying there's only one possible way to transition. And the way we're going to specify that is by saying we can now transition to a set of states, and we're gonna make a state that represents a set of those states. So after an NFA reads a string, how many states can it be in? Arbitrary. We don't know. Up to the number of states in the NFA. It could be in any of them, depending on the structure of the NFA. So some subset of the available states. So now we're going to make the concept of every possible subset of states is going to become a new state, but we may not actually need all of them. So we're going to use this algorithmic process as a way of generating new states when we need them, rather than taking the entire power set of available states from the MFA. So that's the basic idea that I said. We're going to be making subsets of states in the NFA as states in the DFA. Does that process result in a DFA? The answer is yes, it does. Then what is the worst case for the number of states in the associated DFA? What is that boundary? The number of subsets, the power set of the cardinality of the power set of the number of states in the NFA, if we're going back to discrete terminology or set theory terminology. So 2 to the power of the number of states in the NFA, which is just the rule for the number of elements in the power set of a set. A lot of talking, a lot of abstract. Let's give you an example. Here is an NFA. If we want to convert this into an associated DFA, let's first talk about a couple of considerations. So we see that the initial state in the NFA is Q0. This is actually wrong. Gotta make this change before I publish these. But any state that's possible via a lambda transition from that initial state. So if we had something like a lambda transition from here to here, we do that, then the initial state in the associated DFA would be a state called the hybrid Q0, Q2. Because where could we reasonably be starting from? We could either start from here or teleport from here to here and start from here. So we're going to assign the set of all possibilities of the starting state based on wherever you could get to in the NFA without consuming a single input character of the string, in the input string. Does that make sense? Luckily, we don't have that here, but that is an important addendum that I will go fix. So something like, if we have a transition here from Q0 on an A, means that we would come into Q1, but we could also lambda transition from there to Q2. So the transition, if we were doing this in the DFA, would be a transition from Q0 to Q1, Q2. This subset of states in the NFA that we could be in after we made that transition. This hybrid state is a final state because at least one of the states that you could reach was final. And as we know from an NFA, it doesn't matter if you have a single transition to acceptance and 10,000 transitions to rejection, because there is a single path that could be accepted, it is accepted. So let's actually go through this process. The way we're going to convert this into a DFA is we're going to start with an initial state that is exactly that. The initial state is every state that we could get to without consuming an input character. That is just Q0 here. In order for this to be a DFA, there need to be transitions out of Q0 on both an A and a B. Let's start with the one that's actually in the NFA. For an A, as we said here, we're going to make a transition on an A to what we're going to call a hybrid state, Q1, Q2, and it's final. because at least one of the states that you could get to in this NFA on an A was final. So this hybrid state, Q1, Q2, is also final. Last part of Q0, what happens from Q0 on a B? Immediate rejection. So this is how we're going to define a trap state. A trap state is a place that we cannot get to in the NFA. So we're going to just draw an arrow on a B to a state that you can really call either the empty set. I'm just going to call it the empty set. There are no states in the NFA that we can get to from Q0 on a B. So the state represents the empty set version of the power set of these three states. This one's nice and easy because on an A or a B, the trap state just goes back to itself. Now we need to figure out the transitions out of Q1, Q2. To do this, we're going to look at where could we be? What are the set of states that we could be in if we were either in Q1 or in Q2 and read an A? What's the answer to that? Question or an answer?
Answer.
Answer. Go ahead.
Q1 for the empty set.
So we could either be in Q1. If we were in Q1, read an A, we'd be in Q1. If we were in Q2, read an A, we wouldn't be able to do that. That's okay. But we could also read an A and teleport. So this tells us that the set of available states that we could be in, if we were either in Q1 or in Q2 and read an A, is Q1 or Q2. So this actually loops to itself on an A. Questions on any of that logic to derive that? That's one of the more complicated things we've done so far. Yeah.
So the teleports can happen immediately before or after consuming any character. Or you
Yep.
don't even need to consume a character. It
Correct.
happen
Yep.
in both DFA and NF.
Well, we're constructing a DFA out of this. Note that I'm naming these states based on sets that were here, but there's nothing that says that this isn't just Q1 or Q3 or some other set. To be equivalent, it doesn't matter the naming scheme or system for this, but I'm naming it based on the states here so that we see the transformation unfold. That is a really good point. Yes, we can make that lambda transition at any point in the middle of our work. We're in Q1 at any point, we could also be in Q2. What happens from Q1 or Q2 on a B?
Does it go to Q0?
Yeah, it goes to Q0. Because here on a B, nothing happens. Here on a B, we move back to Q0. So the only state we could still be in after reading a B from either being kind of at the same time in Q1 and Q2 is we could only be in Q0 or have something dropped. So this state will transition back here on a B. And it turns out now there are arrows out of every state for every character. So we terminate. We're done. This is the associated DFA for that NFA. We did not need to use all of the possible states from the power set of these states. To give you a sense of what we could have needed to do, we could have needed a state for the empty set, a state for only Q0, a state for only Q1, a state for only Q2, a state for Q0, Q1, a state for Q0, Q2, a state for Q0 or Q1, Q2, and a state for Q0, Q1, Q2. And this would give you the 8 possibilities of the power set of 3 states. These are all the possible states that the DFA could have included. It turns out we only needed 3 of them. This is why we go through this iterative process rather than drawing out vertices for all of these, because a lot of them will just end up being disconnected from the rest of the graph. No way to get there. Questions on that process? Yeah.
If instead of like the first starting like Q0, if you had a lambda transition going from Q0 to Q1, you have a starting space that was Q0, Q1, I guess. Like,
Yeah. Yeah, that would be the name of this initial state, would be Q0, Q1. As the starting, because you could start after having teleported in any of those states. Yep. Yeah,
If you had a Q three with a lambda from Q two to Q three, would you conjoin Q one, Q two, and Q three into one?
you could.
Well, then how do you decide, like, if Q three has a B to somewhere that's not Q zero, how do you decide where the B should go?
In parallel. Because it's non-deterministic. At least the original one was non-deterministic. We would say, we're doing all of them in parallel. And in the DFA, we would need to come up with this set of possible states, because in the NFA, you can think of it like you've cloned yourself. You're in 3 different states at the same time. So this is time step T sub 6. Who knows what actually time step it is? At time step T sub 7, the question is just where could we be? If this, there's no way to get from here anywhere at time step T7. This, there's nowhere to get, and this can get to one particular state on that particular symbol. Then at T7, regardless of where you were, you know that this all kind of comes together, and the only state we could be in is that state. But if this could come to, let's say, 2 more states, because it's an NFA, then we would have these 3 states as the possibility. So we would need to concatenate all of these, and basically at time step T7, we're again in another multi-dimensional state location, I guess. Does that make sense, or did I confuse you more?
Yes, and yes.
Yeah, they're not mutually exclusive, it doesn't matter. Yeah,
So how do we logically go about deciding if we can join the 2 states from the NFA into one state?
it's a matter of whether you can be in both states at the same time.
Okay,
If, for instance, Q1 and Q2 are just naturally linked together in this NFA. If you can be in Q1, you can also be in Q2. But if you're in Q2, you can't necessarily just be in Q1 or also be in
if you
Q1.
were to add like a Q3 after Q2 with a lambda to that one, and then and then draw out an arrow from Q3 to Q1 with a B.
On what character?
It would be a B. You couldn't have that become one state, right?
So Q1, Q2, Q3 could absolutely be one state, meaning that you could be in any of those states at the same time. So if we transition from Q0 on an A, you could either be in Q1 or teleport to Q2 or teleport again to Q3. So Q1, Q2, Q3 would be one state, meaning you could be in any one of those 3 states at that particular time step.
So on the DFA, how do you decide where to have the B arrow coming out of that?
So for here,
Yeah. if you were to add-
because in here, you're either in Q1 or Q2, you're kind of in both at the same time. If you do that, then you read a B, what is the set of states that you could be in? If you were in Q1, you're out of luck, or you'd have to lambda transition to Q2 before you read the B. If you're in Q2, you can get to Q0, but not anything else. So that tells you the destination, the set of states that you could get to on consuming that B. If there's a version of you over here and a version of you over here, and you say consume a B, and then you ask, all right, for all of the clones who just did that, where are you? You would be collecting data from each of those people to say, where are you? And that would come up with, well, only one of them survived that, and they're in Q0. Great, arrow from Q1, Q2 to Q0. One way to think about it, murdering clones.
So then is it safe to assume that if there's a connection between 2 nodes via lambda, then you can combine them?
No, because if you're in Q2, you can't necessarily jump to Q1. So if you're in Q1, you're also in Q2, but if you're in Q2, you're stuck there.
Okay.
That would be true if there was a lambda to and a lambda from, then it's the same state.
Given his addition with the lambda transition and the B,
Yeah,
wouldn't that be true that you can go from Q2 to Q1?
yes,
On consuming?
on a B, yeah. So then the state here, instead of being back to Q0, we make another state that was Q0, Q1. The set of possible states that you could be in. If you were here and consumed a B, you could be in Q0. If you were here and consumed a B, you'd be in Q1. So that's set of states, Q0, Q1.
And that would also be final, because Q1's final.
Yeah, yeah. How are we doing? Those who had their caffeine and those who don't, it's apparent from your faces, I'm kidding. Get it?
And basically terminate before they finish the string, right? Or no?
Yeah, you cannot terminate before you finish the string. So wherever you end up at the end of a particular string, this would tell you that these are equivalent for any particular. Maybe we should go through an example of that. That seems like a good. Someone give me a string that's in A, B star.
A, B, B, A.
A, B, B, A. So in this NFA, we're trying to see, is this string in this language? So looking at the NFA, we take this A, and then we could be in either of these places. We see a B, from here or here, the only place we can be on a B is back here. Now we see that second B and there's nowhere to go, so we immediately reject. From the DFA, now we don't have to worry about parallelism or being in the same location as someone, as another one of your clones, or whatever, however we want to think about that. You just see, you start at Q0, you read an A. You go to the state called Q1, Q2. You read a B, you go back to Q0, you read a B, you go into this trap state. This is where the NFA fell off and just immediately rejected, but we know this is a trap state. No matter what comes after this is going to lead to rejection because we're just going to stay in this trap state, ending here at the end of the string, which is not a non-final state, so we reject.
Sorry, sorry. Once you like, so after the first A, in the NFA, once you have get the first A and you move on to the B, like it just fails because like it's the next one isn't like a B or something like that, or?
It's the second B that causes the fail. So we can, A, we're here, we're kind of in both of these at the same time. On B, can't get anywhere from here, but we can get somewhere from here, goes back here. But now on the second B, there's no transition out of Q0 defined on a B, which is legal in an NFA. We don't have to specify every transition. But if we don't specify a transition and we want to take that transition, we just stop and reject. Think of it like terminating your program in the middle of it. It doesn't complete because you killed it in the middle. You could wait for it to complete. And it would just give you, it's not defined what to do here. So you could think of it as kind of like a segfault. But if you defined what to do, you would just be throwing some kind of exception. It's not like the program would finish with a real answer anyway. It would complete, and then it would say something happened. I can't actually determine where to go. All right. Walk you through this whole thing. So we end up with all of this. I've already talked about it, but there we go. That should be what I drew. Ready for a practice problem?
Yeah.
All right, I'll get you started on that. Here we go. Here is an NFA. Convert this into an associated DFA. So I'll get you started with the first step. What is the initial state of the DFA? Q0. Any other state, we can't lambda transition anywhere in that, so we're okay. So we're just going to say that we start in Q0. But now we need edges out of this vertex on a 0 and on a 1. Watch out for those multi-edge labels, as well as the ability to, in Q0, be in multiple different states on a 0. Very quiet in here. Feel free to work with your neighbors if you'd like. Verify your answer with it, if you have an answer.
Just not sure how to.
Sorry?
Yeah, not sure which group I'm about, like me, or was like zero and ones on it, I don't. It's weird to me, it's like you could either go like, if it's a zero, then it's zero or one.
Right, think of it as doing it in parallel, rather than searching and determining, well, I could go down the path that I'm in this state, or I could go down the path where I'm in that state. You do them both at the same time. Yeah,
Zero that like self loops, is that kind of just saying that if it's an empty string? Or is that saying that if the input's zero, then the NFA?
this is allowing us to have any number of zeros before the one that allows us to accept. So you can think of the actual set that this would accept is 1, 0, 1, 0, 0, 1, 0, 0, 0, 1. Once we leave Q1, we never come back to it. So there are a couple of unnecessary pieces of this, like this loop on a 1. It's not strictly necessary logically, but it creates some slight difficulty, just a little bit, for this conversion, which is why we care about it. Yeah.
Because in the NFA, would zero be valid within the sling, because we could be either in an unquantified state or a terminating.
Yes, it is in. As long as there is one path to acceptance, you accept, even if there are 10,000 paths to rejection. Or more than that.
Like, I think I finally understand like what the NFA is doing.
Hmm.
Now this is like, how do I translate it like just think of the
Loop the process of, as long as there aren't edges out of one of these, figure out what those edges are. Let's do Q1 first. Q1 on a 0, what are the set of states that we could be in? Just Q2. We can't get back to Q1, we can't go backwards to Q0, so we can only get to Q2 on a 0. There is no Q2 yet in this, so on a 0, we're going to transition to a new state. So Q2. What about Q1 on a 1? Where can we be? Just Q2. So we can now make a multi-edge there. What about Q0, Q1? What about, how do we show a transition from Q0, Q1 on a 0? Where could we be? If we were in Q0, we could loop to Q0. If we were in Q0, we could move to Q1. And if we were in Q1, we could move to Q2. So there is a path to be in all three states from Q0, Q1 on a 0. Since there is no state Q0, Q1, Q2, you're going to make it. Very wide one. It's also final. On a 0. What about from Q0, Q1 on a 1? If we were in Q0, we would be in Q1 after that. If we were in Q1, we'd be in Q2. So we need a state that is Q1, Q2. And that becomes where this goes. On a 1. There's still work to do. We need to figure out what the out edges are for all three of these vertices. So let's start with Q2. That seems like it'll be a little bit easier. On Q2, where can we be on a 0?
In a trap state.
In a trap state. So we need some state that is going to be the null state that we transition to from Q2 on a, it was on a 0. On a 1. Q2 on a 1, we can go back to Q2. So we will loop Q2 back to itself on a 1. That state's done. The trap state should also have all right, from Q1, Q2, where can we get on a 0? Just Q2. The only time you go to a trap is if there's no option. So Q1, Q2 will go to Q2 on a 0. And on a 1. No, yes. Yes. That's still Q2, both 0 and a 1. Now we just need Q0, Q1, Q2. Where does that go on a 0? If we could be in any three of these states simultaneously, but also have to take an edge that has an edge label 0. We could be in Q0, we could be in Q1, or we could be in Q2. So we're going to loop to itself on a 0. Where could it be on a 1?
Either Q1 or Q2.
Q1 or Q2. That state exists, we'll transition there on a 1. We did it.
This looks like a mass of spaghetti.
Yeah. I tried to draw it in a nice circular way where stuff that we would need to. I had a sense of what this would look like at the beginning, but if you don't have that, it can absolutely start to look like spaghetti. So finding a way to redraw your graph vertices in a way that makes it more readable can actually be very useful. If I'd drawn this in some other way, it would look really gross. It already looks pretty gross, but even a simple NFA like this can have some number of states that very quickly approaches the power set of the number of states in the NFA. Yeah.
Couldn't you just do a self loop with Q0 and Q1 to be 0, and then just have the 1 that goes to Q1 and Q2, and then you can just get rid of the Q0, Q1, Q2.
Q0, Q1 on a 0. If we're here, we could be here. If we're here, we could be here. And if we're here, we could be here. So I don't think we can self-loop here because we could also be in Q2. So we need to specify the state that represents the state that you could be in all three of these states. Does that make sense?
Not really.
So maybe walk me through your logic of starting right here on Q0, Q1.
Well, my logic is that basically that it feels like that's just like an unnecessary step in the middle, because if it's a 0, it's gonna go there, but if it's a 0 there, then it's just gonna self-loop, like if it's 5 zeros.
Like 0 here and then here?
Yeah, then there'll be whatever, 3 more zeros right there, and then if it's a 1, then it'll go
Yeah,
that
there's
way.
no way to really specify it. Ignore all zeros until you see a 1. That would be some piece of logic that I would love to be able to.
No, I'm not saying that, I'm saying more of just like, couldn't you just repeat as many zeros as you want in Q0 and Q1, and then once you get a 1, go to Q1 and Q2 without having that intermediate step?
I don't think so.
The graph is just listing all states it could be in, it's not necessarily efficient
Yeah.
states that it could be in.
Yeah, there's additional logic that you would have to read, like the entirety of this edge and this state are unnecessary. The reason being, once you leave this final state, you cannot get back in a final state. So this might as well just go to a trap state.
Really should just be.
It really should. The reason to design something like this is to be able to create something like this and to show how that would work, even though logically, there's really no reason to have this. But since we do have it, there is exactly one DFA that represents it. If this led to a trap state, the DFA that we produced would be different. And in fact, the next thing we are going to talk about after this is constructing a minimal DFA. So how could you note that, for instance, this could turn into this, but there are some inefficiencies in this in terms of we could create exactly this logic in a simpler way. Just wanted to show something that was a little bit more complicated to show you what that process would be like. Questions? Anything I can clarify about this process? All right, I will actually show you the solution on the slide, but it should be exactly this solution. We got to the midpoint, and there's the full solution. Note how the names of these states here are sets. That helps to clarify that these states are coming from sets of states in the NFA. You're welcome to do that if that makes it easier for you. You do not have to. I know what you mean if you just concatenate the names of the states, but they represent comma-separated sets of the NFA states. Here is the actual technical algorithm. If you would like to actually write it, this is what it would look like in a textbook. I much prefer the visual way of thinking it. Looking at this, it takes me a while to come up with the intuition that is on the board, but create a graph with a vertex, identify it as the initial vertex, repeat steps until no more edges are missing in the graph. Any vertex that has no outgoing edge, find what those edges are. So what happens outgoing from that on every character in the alphabet? Come up with a new sequence of states that you would be in. This is talking about the union of all the transition probabilities. So if there is some way to get from some state Q sub I on an A or Q sub J on an A, etc., then we say if there's a way to get there on an A, then we're going to put them all in the final answer for the vertex that we need to transition to. So we will create a vertex in the graph, or if it already exists, just put the arrow there and label it. Continue that process in a loop until no vertices are missing outgoing edges for any character in the alphabet. How we doing? Show of thumbs maybe for how we feel about this NFA to DFA conversion. Lots of sideways. That makes me think we're going to want another example of this. I don't have one planned, but I can make one from the next homework assignment or one of those extra problems. Maybe I'll do one of those in class as we get closer to assigning that and going in and doing it. So we are starting to cover content from the next homework that'll be due a week from Wednesday. With the last couple minutes, I'll at least introduce the next idea. I did not prepare it. So as I alluded to, we're going to start figuring out how to reduce a DFA into a DFA with fewer states. Reason for this is we know that there are really, as long as it's an infinite language, there are an infinite number of DFAs that can represent that particular language. Just like with code, there are an infinite number of algorithms that you could write, at least sequences of statements in a particular language that are the same algorithm, but they would have vastly different complexities and take a vastly different amount of time to run. We want to be able to compare DFA to DFA, which one is simpler, which one is better, and are they the same logically? So what variables would we have for this? It really comes down to the number of states that are in the DFA. If there are fewer states, then you get faster acceptance, and it takes less memory for you to represent the DFA when you go to put it in a computer in some way, shape, or form. So less storage space is the main guarantee that we get from having a better DFA, smaller DFA. So giving you an example here, Can this DFA be reduced? There are some obvious and some less obvious reductions that we could make to this. See if you can come up with some of them.
Five has no way of being reached.
Yes, since we cannot reach Q5, nothing about Q5 or any transition out of Q5 matters. This can just go away. Since we start here, we need a way to get here in order for this to be relevant.
Honestly, Q3 doesn't necessarily seem necessary either, because you could just cram it down to one Q4 final state because it's a trap state anyways.
Okay.
So why do we need two separate trap states if it's 0, 1 versus 1, 0? Or 1, 1?
How would we, in this way,
If we go 0, 1, we enter a trap state where it doesn't matter, we're in a final
Right.
state versus 1, 1, it's a final
yeah,
state.
there's something that seems a little bit fishy about how similar these are, but we don't really know unless we can show logically that there is no way for us to reach Q3 in such a way that we couldn't also reach Q4 if we redirected some of the arrows to remove one of these vertices. So this is the less obvious reduction, is one of these states is not necessary. But how would we actually show that? You can get an intuition for it, but you really need to know if you're gonna get rid of a vertex, that you're not changing the underlying logic of the language that this accepts. Yeah,
Can you get rid of both Q3 and Q1?
get rid of both of these?
Yeah.
Intriguing. If we did that, so we know that 0, 0, 1 is accepted.
Yeah.
How would we,
You can have like Q1, have 0 and 1 both go to Q2 and.
yeah, if we keep this, I think we'll be okay.
Yeah.
But I don't know if there's a way to get rid of Q1. In fact, this process will tell us.
Trying to think like, what exactly is this what exactly is like it checking for exactly?
We want the minimal DFA. We want to represent the logic of the language that this accepts with the fewest number of states. So we will come back tomorrow and we will figure out exactly how that works. I can answer questions though, if people pack up.
You make Q1 to Q2 and multi-edge.
You could, yeah, doing this on a 1, but a 1 from here is immediately accepted, whereas a 1 from here wouldn't be.
Trying to think like the top row, it's like 0, 0, 1, and then 0, 1 is allowed 0.
Yeah, 0, 0, 1 is also allowed. We go here, here, here.
Yeah, 0, 0, 1 is allowed, but also 0, 1 is allowed.
But 0, 0 is not, so we can't redirect the 0 to here, because then 0, 0 would be accepted. I think that ended up being the answer.
Like somehow it's super nice and then it's allowed.
Yeah.